There is a small river that flows through the town of Greater Napanee. Folks say this river is different. It has a tide as high as 2 feet, and it cycles about every 2 hours. Experts say it is because the river resonates with the regular sloshing in Lake Ontario. I wanted a more complete explanation, but there was very little information available. In 2017, I placed some pressure data recorders in the Napanee River and the Bay of Quinte. The blue and red lines in this graph of pressure, which is a proxy for water depth on the vertical axis, against time on the horizontal axis. The yellow line is from government data for levels at Kingston. Each of these wavy lines represents a similar sort of rise and fall of water levels, but each of these occurs in very different water basins that behave in distinctly different ways. Lake Ontario is huge and its surface oscillations can often be complex, but keep this simple water teeter-totter behavior in mind when looking at lake level data. A sudden change in the wind often causes the lake to move like this, with opposite shorelines alternately rising and falling between 1 and 6 inches in a bit over 2 hours, far less than the choppy surface waves. This is a simple standing half wave that is represented by the yellow line in the graph. The rise and fall of Lake Ontario creates a similar rise and fall at the entrance to the Bay of Quinte, called the Adolphus Reach. This travels as a wave through the bay and can be seen as the slightly larger level change of the red line from the long reach data. The data from 2 locations in the Bay of Quinte, in the long reach and just west of Belleville, depict action from this type of traveling or transverse wave. Somewhat like when you flick a long rope and the bump in the rope travels along its length. These long, slow waves travel one way through the bay, starting at the lake end to the east, on to the west end some 80 kilometers away. It's a sort of message from the lake that takes about an hour for the 2-inch rise in the lake to show up as a 3-inch rise in the long reach 28 kilometers away. About 40 minutes after the 3-inch red line maximum peak from the long reach location, the river level in Napanee, shown as a blue line, peaks and then drops 10 inches, then rises 9 inches, then falls 8 inches in a tide-like behavior. This is a standing quarter wave. Think of this as the Napanee River's surface level oscillation, which resembles a conventional tide. A small rise of water in the Bay of Quinte on the right at the mouth of the river, causing water to rush in towards Napanee 8 kilometers away on the left. Then an hour or so later it rushes out again. Most of the tidal water flow or current is at the wider mouth end of the river, while the greatest change in water level is at the narrower Napanee town end. Because this part of the river is long and thin and protected from the wind, it tends to store this tidal energy for many cycles and have its own almost fixed natural oscillation period of between 2 and 2.5 hours. This happens independent of the watershed flow in the river, which changes more slowly over long periods of time and has only been seen to flow in one direction. The standing half wave in the lake, the transverse wave moving linearly through the bay, and the standing quarter wave in the river are the 3 waves that may best characterize the source and behavior of the Napanee tide system. That is a light summary and may be enough for most folks. If you're willing to risk witnessing a tidal bore, then continue on. Next, I'll give some background on the locations, then the graphs that follow will perhaps help to describe the scale, frequency, and the tide, and connect the dots with the distant forces that cause it. I'll finish with the leftover mysteries about some of the tide's irregular behavior and its possible uniqueness in the world of freshwater tide-like oscillations. This project is an exercise in exploring nature. This video will only scratch the surface of what could be said on this topic. Be prepared to use the pause button if you want to ponder the graphs. Most of the vertical axes are pressure in millibars, where a change of 10 millibars is approximately equal to 4 inches of water. Please leave comments and let me know if I made a mistake or wasn't clear. Below the waterfall in Napanee, the last 8 kilometers of the Napanee River is a flat water section that connects to the Bay of Quinte and out to Lake Ontario. In the spring of 2017, as lake levels rose to record levels, the oscillating tide in the river regularly rinsed the docks in the town of Napanee. Soon after, signs were put up warning of rapid water level changes. The wet docks may be new, but the tide is old. There is a plaque by the river celebrating a well-known citizen, H.M. Smith. He spent several days measuring the rise and fall of the river and graphed the results. He wrote about it for the Ontario Sailor magazine. Both are available at the local archive. Here is a quote. "The outgoing tide was falling rapidly and lowering the water level an astounding 28 inches in an hour and 20 minutes, and we both watched 2 more complete incoming and outgoing tides, the range of 23 inches. Lake Ontario is one of the Great Lakes of Central North America. It, along with the Bay of Quinte and the Napanee River, make up 3 parts to this story. This shows that the eastern part of the lake consists of a deep basin to the south, in dark blue, and an area to the north that is relatively shallow, which connects to the Bay of Quinte and the Napanee River. The shape and form of all these bodies of water play a role here. The thin red area at the top of this picture is the Bay of Quinte. The Bay of Quinte is about 80 kilometers long with side bays and river inlets. The Napanee River between the waterfall and the bay is an 8-kilometer long, shallow channel. Here is a look east towards the falls from the Centre Street Bridge in downtown Napanee, and a look west towards Conservation Park. Again, this is the eastern end of the lake. The yellow tacks are locations for climate and lake level data from government sources in the USA and Canada. The red tacks mark places I collected level data. Also, Environment Canada archives radar images which cover this region. This shows the Napanee River connects to the Bay of Quinte roughly midway along its 80-kilometer length. The water surface levels at Cape Vincent, Kingston, and the entrance to Adolphus Reach all rise and fall at roughly the same time. That sends a pulse that travels linearly into the Adolphus Reach. It shows up as a level rise on the sensor located in the Long Reach, 28 kilometers away. It continues on into the bay past the sensor west of Belleville, 35 kilometers farther on. Napanee is about 14 kilometers from the sensor in the Long Reach. Here is a plot of the surface levels over most of 8 days in May. It is fairly representative of the behavior of the river when the winds in the region are not stormy. It shows the rapid changes in surface levels. The general spikiness is fairly consistent in frequency, but the amplitude varies a lot. I've circled a couple of exceptions where the pattern breaks down somewhat. It shows roughly the last half of the previous graph and is shown here with some areas circled. Area 2 with 8-inch oscillations and Area 4 with up to 16-inch oscillations have in common a somewhat smooth and regular consistency. They emerge following periods of smaller oscillations with less consistency, like Areas 1 and 3. This is a common pattern. To help understand how the tide comes about, we can look at some Department of Fisheries and Oceans data recorded in Kingston. They record levels so that surface waves do not bias them. This graph shows the Lake Ontario levels in Kingston during the same time period as the previous slide. The circled area has a maximum change of about 4 inches. It also oscillates at a similar rate to the river data. So 3 or 4 inch change in the lake correlates to a latter 14 to 16 inch change seen in the river. The rest of the data shows smaller oscillations and more variation in rate and is more difficult to correlate. In this time period, the tides and winds were moderate, and it is difficult to clearly link them. For this reason, I'll look more closely at larger tide events and try to correlate them with wind data from the National Oceanic and Atmospheric Administration in the USA, like that shown above, and also Environment Canada data and radar images. Hourly lake levels for a full month are available and updated every few hours. Often the ups and downs are minor, as in the previous example, but this graph points us to a day where there was a larger change. That's on June 25th. Graphing 3-minute interval data for that day shows that early in the afternoon the lake level started to oscillate more, changing a tenth of a meter or 4 to 6 inches in an hour. The second high peak in this graph is the same as the 5
5:30 peak of the red line in the following graph. The blue line shows what is happening to the river levels in Napanee. 3 hours after the peak in Kingston, at 5:30, the Napanee peaks. The level in Kingston drops about 8 inches in the hour after 5:30 p.m. In Napanee, the river drops about 20 inches in the hour after 9:30 p.m. Let's see what the weather is doing. Oswego, New York, records 2 sudden increases in wind speed in the late afternoon. Also, a single rapid peak and decline of wind speed in Kingston. In this radar animation from the afternoon of June 25th, the blue-green portions represent precipitation associated with storm systems. You can see 2 separate storm cells passing over the northeast and southeast part of the lake, which caused these winds and in some way combined to likely cause the lake sesh and ultimately the increased amplitude of the Napanee tide. On July 20th, the same sort of oscillation shows up in the hourly lake data. This time we'll start with the weather data. A larger rainstorm is crossing the entire eastern part of the lake. As this storm passes, the wind in Oswego shifts quickly from a north wind to a south wind between 1 and 2 p.m. The wind speed in Kingston shows a quick peak at this time. Because the force of the wind increases with the square of the velocity, this represents a 4-fold increase. The sudden change in the wind just after 1 p.m. causes a quick 6-inch drop of the lake at Kingston after 2 p.m. This turns into a regular sloshing of the lake of 3 or 4 inches that goes on for about 12 hours. Around 2 hours later, the Napanee River level begins changing 12 to 18 inches and goes on for another 14 hours. Comparing the mid-Napanee River data to the data from the river in town generally shows that the rise or fall is at least 50% greater in town. So this is now August, and here we have another event, this time on August 4th. Again, the radar shows a series of storms passing over. The storm brings a sudden change in wind speed and direction, starting at 3:24 p.m. Fairly steady light south winds switch to stronger west winds. This creates a pattern in the surface levels that can be seen repeated as it passes through the Bay of Quinte. Kingston wind speed data shows 2 slow peaks on the left and a W shape of 3 or 4 rapid peaks on the right. The following slides of surface level data shows this pattern too. So if we notice the 8 p.m. peak in Kingston of about 6 inches, we can follow it as the start of a W shape through to the other locations in the following slides. Notice the brief peak before it. The spike will get filtered out by the long reach data location. Also notice the 2 slower peaks on the left. Although the data is of poorer quality, the pattern and timing is roughly the same at the entrance to the Bay of Quinte, called the Adolphus Reach. It and the long reach that follows it have extended portions with somewhat parallel shorelines like a giant canal. Halfway down the long reach, the pattern is clear, widely spaced peaks followed by a rapid W shape. It has taken about an hour to get there from the lake. A 6-inch level change in Kingston is now a 7.5-inch change. The same peak is evident halfway up the Napanee River towards town, around 40 minutes later. I'll come back to this. About 3 hours later, the pattern is weakly repeated a little west of Belleville. It has traveled about 60 kilometers from Lake Ontario. It is somewhat distorted and diminished, but the 2 slower, widely spaced peaks are clear, as are some of the more rapid ones of the W pattern. The point here is that the Bay of Quinte is a one-way street for long wave patterns that travel into it from the lake at Adolphus Reach. These waves are maintained or improved somewhat on their way through the canal-like portion to the mouth of the Napanee River. After that, they dissipate. Going back a slide to the mid-Napanee. What's important in this slide is that the W pattern is just like out in the long reach, but small bumps shown circled appear between the wider, more spaced peaks. This is likely because the Napanee River oscillates at its own natural frequency, which more closely matches the 2-hour frequency of the W pattern. The linear momentum of the water in the river, raising and lowering the level, keeps itself sloshing. Often the big lake matches the river's frequency, but sometimes it doesn't. Below the falls in Napanee, the river or estuary is like the Bay of Quinte, an extension of Lake Ontario. The data in the previous slide shows that it behaves differently. The bay has peaks and troughs that travel from the lake down through the bay. A second one can start before the first one has reached the end or dissipated. Below the falls, the Napanee River rises and falls almost as a whole. Water is flowing in from the bay and then is flowing out to the bay over and over again, sometimes synchronized with pulses traveling down the bay and sometimes not. The river has its own momentum, which makes it a more regular slosher than the lake and the bay, which cause it to start. In September, there was an extended period of warm, sunny, and calm weather. This time is a good example of sort of baseline behavior of the system without storms. In calm weather, the river in town still shows a clear oscillation, an amplitude as low as 1 inch and as high as 4 inches on this day. The first 3 cycles of this plot are shown in the next slide, along with the matching mid-river data. The upper blue plot is in town, and the lower red is mid-river data. In this plot, the mid-river max and min points occur between 9 and 15 minutes before the corresponding points in town, 4 kilometers away. Typically, the level change is at least 50% greater in town, but sometimes close to twice as much. This portion of the river is filling up and draining out as a whole. The momentum of the water and the narrowing of the river cause it to pile up higher and on the way out, drain down lower at the town end. The river clearly maintains this wave-like pattern more consistently than the lake does. In October, the weather is more unsettled and windy. I'll have a look at October 11 and 15-16. On this day, there were no sudden changes in wind direction. It was fairly steady out of the northeast, but they slowed around 3 p.m. Again, there is a rainstorm passing through, but it hangs around, a bit different from the summer storm fronts. A 4-inch W-shaped sesh pattern appears when the wind drops off. The same pattern is clearly seen passing through the long reach. 4 inches increases to 6 inches. Notice the small peak in the middle of the W. A W with a tall central peak is what is seen in Napanee. The outside edges have increased by a factor of 3 or less, while the central peak is increased by a factor of 8. Reminds me a bit of a dad who forgets just once to keep pushing his kid on the swing set. The river, a bit like a pendulum, can store enough energy to keep it going strong for at least one cycle. The evening of October 15 sees another storm front passing by the region. Oswego, New York records show a sudden change in wind speed and direction. Water levels at Cape Vincent, New York show a clear but brief high double peak. Kingston levels are similar. The drop after the first peak is around 7 inches. The drop after the first peak in the long reach has increased to 10 inches, but there are only 3 clear peaks before it all but disappears for a while. The same drop after the first peak is now 24 inches, the largest recorded during this project. The tide diminishes in amplitude, but doesn't stop like out in the long reach. This is perhaps best explained as the pendulum-like behavior of the standing wave sesh out in the lake, but more durable here in the river. This is a graph which looks at the timing around that first big drop in levels, with the long reach shown in orange and the Napanee in purple. The peaks were 54 minutes apart and the troughs were about 69 minutes apart. Although it can be a bit variable, the seshes that can be seen in the data from Kingston, or in real time with data online from Cape Vincent, which is the same, roughly, can be seen amplified by about 3 to 5 times about 2 hours later in Napanee, especially if they are around the 2.5 hour wave period to match the river's natural oscillation. Once again, in November, we have the hourly Kingston levels. We'll have a look at the big peak on November 9th. With a similar wind profile, we see quite a similar double-peaked sesh. Kingston is at the east end of Lake Ontario, and with a strong west wind piling up water at that end, you can see the equal and opposite drop in levels at Burlington at the west end of the lake. Again, the constant feature of this project has been a storm front trigger. The wind profile from Oswego is very similar to the one from October 15th, a sudden increase in wind speed and a shift in direction to a west wind. This time we see a single large tide oscillation of over 20 inches and an irregular pattern of smaller level changes. No resonance here. Notice the low point before the high point. It is the only thing that might correlate well with the Kingston data in the next slide. The first big swell of water coming down the long reach might be timed or shaped wrong and conflict with the existing oscillation in the river. Points 1 and 2 are spaced about 2 1/4 hours apart, which is close to the average for the Napanee oscillation. 2 and 3 and 3 and 4 are more like 3 hours apart, which would not be resonant. The only part of the lake pattern that is timed with the river pattern is the drop after point 2. It is about the normal average 2 hours ahead of the trough before the single large peak mentioned in the previous slide. Timing is a critical factor that can limit the amplitude and persistence of the tide. So let's have a look at the circumstances that created the big 28 and 23-inch tides that Smith wrote about on the May long weekend in 2004. In the early morning hours, there were some gusty southern winds, and then they shifted to go light out of the north. Hardly exceptional. However, Lake Ontario at Kingston had a steady, large, and repeating sesh from midnight until noon. The frequency was at a reasonable match to the natural oscillation rate of the river. It quickly diminished when the wind shifted from the west. The highest tides may well have extended into the time when the winds were lightest, and left the sailors at the docks in Napanee scratching their heads. So this sesh example may be close to a best case for a resonance-enhanced tide. The 2017 data didn't produce anything as consistent and persistent. It fits with the seshing of the lake from south to north and back, repeating. The lake can also sesh from west to east and back, repeating. The best example was when the remnants of Hurricane Ike passed just north of the lake.
In the early morning hours of September 15, 2008, the remnants of Hurricane Ike caused wind speeds to spike, combined with a sudden drop in atmospheric pressure.
The sesh as measured in Kingston was 18 inches, larger than any in 2017, and the period was 5 or more hours peak to peak. Fishermen and boaters around the Bay of Quinte were commenting on the internet message boards about the strange current and rip tides and level changes. Surely this would have caused some tides in the Napanee River. Perhaps it was the big one that got away.
The wind on April 4, 2018 was stronger than during the remnants of Ike, but it wasn't as sudden, and no sustained east-west sesh occurred. The strong west winds on April 4, 2018 pushed the water up 12 inches around Kingston. This interrupts the more regular sesh pattern in the lake. The two peaks marked with down arrows correspond to the largest river tides in the following slide, which occur predictably about 2 hours later. Right after the second one, a large, slow, non-resonant pulse appears to stop the river tide for 4 hours. In the river, there is a regular tide oscillation circled on the left. It continues to go stronger until, as circled on the right, it almost disappears. The rate of the oscillation has a greater influence on the river tide than the size of the oscillation.
During multiple consecutive large level fluctuations, you can calculate average river flow rates past the mid-river data collection point at the left end of the red area. The area of the surface of the river multiplied by the increase in depth gives the total volume change. Subtract the flow coming down over the falls, and you get the flow from the incoming tide. Large tides can have flows past the left end of the red box that equal peak spring runoff levels of 60 cubic meters per second. This flow then reverses direction every hour. Although this depicts changing salinity in an estuary and river due to ocean tides, it also gives a reasonable representation of the sort of two-way flow that happens in the Napanee River coming from and going to the Bay of Quinte.
Harbors all around the Great Lakes interact with long-wave seiches. The harbors at the mouth of the St. Louis River of Superior, Wisconsin experience 2.1-hour oscillations like the Napanee River. Lake Superior has a natural east-west seiche of 7.9 hours and can cause the St. Louis River to reverse up to 11 miles upstream.
Green Bay in Lake Michigan is the largest freshwater estuary in the world. It has regular seiches of a foot or two that feed into the Fox and East Rivers in the city of Green Bay. The period is usually closer to 10 or 12 hours. It would have slower and likely higher tides than Napanee.
The data I collected showed that the fastest change in water level was around 1 inch per minute. The maximum change in one cycle was about 24 inches. To achieve a 24-inch change, you have to move an amount of water that's similar to a fully loaded freight train back and forth every hour near the mouth of the river. So what is different about this tide? Seiches in lakes are normal. Level oscillations in rivers and harbors caused by seiches are common. The Napanee tide is an intriguing example of fluid wave behavior, but is it exceptional? While these graphs and the data collected can support a description of this tide as I have tried to do, they could also support a mathematical analysis that I have not tried to do. Either way, nothing can be said about the tide being different without recorded examples of many other freshwater tides to compare it to. It is at very least unusual enough, like so much in this world, to be worth exploring. Since true ocean tides are predictable, a little freshwater tide might aspire to being forecast. Because it is a weather-caused tide, it will be difficult. But just for fun, a local weatherman could reasonably say there is an increased probability of tidal extremes around 1 to 5 hours after this storm passes at around 4 p.m. this afternoon. A more accurate tide prediction could be based on the real-time lake level data from Cape Vincent, New York. It is possible to see both the rate and the scale of changes in Cape Vincent, which would likely resonate and result in an increased tide in Napanee. After all, real science is about making predictions. In the future, local tide watchers will follow tidal Twitter alerts. Maybe. So here are a couple of ideas that might be of interest to someone. Inexpensive data logging with online graphing is available and could help draw attention to the river and the town. And art that can change with the tide has been tried in other places, probably not anywhere with a fresh water tide. So that's about it. Just a quick thank you to the people who made their shorelines available for me to set up my data recording equipment, and to the government who makes available their data freely online, and to any people who can explain what's going on in this graph below.